In the late 1800s and early 1900s, there was a lot of activity to try to understand and to model the spectral distribution of radiative transfer from bodies. And so early in this, in terms of pre-quantum mechanics work, was a thermodynamics model developed by Wien in about 1896 that attempted to model the emission using experimental data. And so this Wiens formula was reasonable, was accurate within 1% for very low temperature conditions. And sort of separately, there were electromagnetics type models. Some people would call it equipartition with classical statistics, that was developed by Lord Rayleigh and Sir James Hopwood-Jeans. And so this is sometimes called the Rayleigh-Jeans law. And neither of these models were able to completely approximate what was being measured in terms of the spectral distribution of blackbody radiation. Planck, interestingly, used the same approach as Rayleigh-Jeans, but used an important quantization of energy rather than equipartition, and because of that was able to fit, and it was essentially empirical, the model. So this model that we have today, the spectral distribution of blackbody radiative emission, is given his name and is termed Planck's distribution. So Planck's distribution depends on many different factors. So among others is what has become known as Planck's constant, h. Another is Boltzmann's constant, and of course the speed of light in vacuum. You also see inside here the wavelength and the temperature. So the thing about this that's interesting is, first of all, to understand what this distribution looks like and to understand how this distribution is used in the radiation heat transfer modeling. In terms of the spectral hemispherical emissive power, we know that the spectral hemispherical emissive power is dependent on the spectral hemispherical intensity through this pi I lambda b. I guess said differently, we know that if I lambda directionally is diffuse for a black body, then we can use that information, I lambda b is diffuse, then E lambda b, which is the black body, is just pi I lambda b. And so in terms of that, there have been, sort of a collapse in terms of the parameters, and the collapse in parameters is just that we have what are known oftentimes as Planck's first constant and Planck's second constant to parameterize this equation. So the Planck distribution, or Planck's radiation law, has an interesting formulation. What we see here is wavelength in meters, and so the areas of interest for us, of course, again, are micrometer type ranges. So we are typically in this 0.4 to 0.7 micrometer range, which we understand corresponds to the peak in the visible spectrum. So let's take a look at this. This is 1 times 10 to the minus 6. This is 2 times 10 to the minus 7, 3 times 10 to the minus 7, 4 times 10 to the minus 7. So 4 times 10 to the minus 7 is 0.4, 5, 6, 7. So 7 times 10 to the minus 7. So we are in a wavelength interval that looks like that when we talk about visible radiation or visible light. So it's 0.4 micrometer to 0.7 micrometer. We see that this corresponds. So these are what we're showing here are different temperature sources. So this is T source, and for a particular T source, this is the emission from it. And what you see in terms of that emission is that at 5800 Kelvin, that the temperature at the peak is roughly between the 0.4 and 0.7 micrometer. Well, this 5800 Kelvin is the black body temperature of our sun. And that's not SON, that's SUN, of Earth's sun, in our solar system. And in general, the peak value at any given temperature sits on a particular curve, which is called Wiens Displacement Law. And Wiens Displacement Law says that lambda max times temperature is about 3,000 micrometer Kelvin. So it's 2898 micrometer Kelvin. This tells you that if you know that, for example, you have a 1,000 Kelvin source, that the maximum in lambda is about 3 micrometer. So let's see if we can find 1,000. So this is 1,000, and the peak is at, so this is 1, 2, 3. So 3, which is correct. So our 3 micrometer condition has a peak for 1,000 Kelvin source. And so this is very useful in understanding the limits of where we sit in terms of wavelength and temperature. So if we wanted to look at the total, which is the integration over all wavelengths, so 0 to infinity, hemispherical blackbody emissive power, we have to construct this integral from 0 to infinity of this Planck distribution. When this is done, this yields the Stefan-Boltzmann law, which is the simple law that we use oftentimes in understanding heat transfer in radiation conditions. It yields that EB is sigma t to the fourth. This can actually be done with Wien's law and the Rayleigh-Jeans laws in a much more simplified manner, and these are moderate. They're not as accurate, obviously, because there are errors in them, but they surprisingly yield reasonable results. But this integration can be done using some variable transformations and using integral tables to identify how this all plays out. We find out that the Stefan-Boltzmann constant, which is sigma, is 5.67 times 10 to the minus 8 watts per meter squared Kelvin to the fourth. What's interesting is that if the spectral emissive power is divided by T to the fifth, so this is not the hemispherical, this is the spectral, we get something that depends only on lambda T and not on lambda or T alone. What this does is it collapses all the Planck distribution curves on a single curve. So what we're saying is that if we're looking at the Planck distribution and we transform it such that we are dividing through by T to the fifth, it's a single curve for all temperatures. And this becomes very useful in terms of identifying, for example, the fraction of radiation within different wavelength intervals. So one of the things that this would tell us, and tables are developed for this, is the amount of radiation that's emitted between 0 lambda T and 2898 lambda T is about 25%. So if we looked at the total area under the curve, we understand that the area under the curve here corresponds to the total amount of radiation emitted in the system, that this is an easy way to collapse this type of value. And so let's think about that differently. So we can think about a band fraction, which is the amount of energy transmitted in a particular wavelength interval divided by the total amount of radiation that's emitted. So this is called our band fraction function. So we're integrating from 0 to lambda, E lambda B, thought differently. So for a particular temperature, we're interested in the amount of radiation to some lambda 1, for example. And we know that if we integrated over the whole range, we get sigma t to the fourth here. As you look at it, there's a d lambda here. To get this to be an integration with respect to lambda t, we have to multiply by t and divide by t. So when we do that as d lambda t, we have a sigma t to the fifth on the denominator. We know that e lambda b over sigma t to the fifth is purely a function of lambda t. And so we have the fact that the integral from 0 to lambda e lambda b d lambda is equal to this band fraction times sigma t to the fourth. So a different way of thinking about it is f of lambda t times sigma t to the fourth. So we know immediately how much radiation has been emitted just by looking at that. The band fraction within a different interval, so if we were interested in the amount of radiation emitted between lambda 1 and lambda 2, we know that we can construct this as an integral from 0 to lambda 1 So we integrate from 0 to lambda 2, and we subtract off the integral from 0 to lambda 1. And so we're just showing that in terms of the fractions there. Tables are available, and this is a table from Inkerper and DeWitt that shows our lambda t function. It shows the band fraction itself. So this is the fraction. And it shows the value of that, the actual, in this case, it has it as I lambda b over t to the fifth, sigma t to the fifth. So this is the curve that we drew in terms of lambda t. And then it has the divided by the maximum value. So here, this is the maximum value. It has this curve divided by the maximum, I lambda b divided by its maximum. So we see that the maximum occurs at 2898 micrometer Kelvin. The fraction up until 2898, until the peak, is 25%. And again, there are tables available to provide this type of information.